So we're going to talk about the concepts of time as it relates to blockchain. And it's actually something that we have found through our project a way of really leveraging. But it's a core characteristic of blockchains that they do have this notion of history, yet it's really considered sort of baggage or kind of this anchor in most blockchains. So the title is Time Travel and Temporal Something. Actually, our communications director came up with that title, and I was talking to my wife last night, and she asked me what I was going to talk about today. And I read this to her, and she said, "Oh my gosh, there's no way you could ever live up to that title." Because, but quite simply, we're just going to talk about traversing back in time. So I'm a co-founder of Fluree and co-CEO. Co-CEO is a little bit of a strange title. The other co-CEO of Fluree is Flip Filipowski. He's a very good friend of mine, and we've been building software companies together for almost 2 decades. Over those past 2 decades, really kind of 3 core companies in that time, 2 of which were founded and became publicly traded on the NASDAQ. One of which became the 8th largest software company in the world at the time of its exit. And our last company was a large global software as a service organization, which we took right up to the point of taking public, as close as you can get, and made some decisions that the markets weren't quite right for it. But the common thread through all of those, and really the common thread through kind of what we're focused on here with Fluree, is enterprise software. So we are huge fans of cryptocurrency. We love cryptocurrency. We participate in the ecosystem a lot. But what we're trying to do through this business is apply blockchain and blockchain concepts in a way that it helps businesses. Okay. So time. So, a core characteristic of blockchain technology is this notion that you have this immutable ledger. And as I mentioned before, a lot of people think of this immutable ledger sort of as baggage. Like, I don't really care that, you had 2 Bitcoins a month ago. I care that you have 2 Bitcoins now if you're trying to pay me. And so we really care more about the tip, sort of, or the current state of the blockchain at any given time. And the baggage is all this history, all this other data that kind of hangs around with it. And that data is absolutely necessary because really without that data, we can't prove the validity of a blockchain at any point in time. But everyone's trying to work around this problem of how do we get rid of some of that data or not need it. And in Bitcoin, we have concepts like SPV nodes. If you're familiar with that, certainly Ethereum, this is a hot topic. Oftentimes they refer it as blockchain pruning, the idea of getting rid of, maybe not part of the blockchain itself, but part of the state around the blockchain. There's even proposals for concepts like blockchain rent. The idea that if you're going to force us to carry all this historical data and we have to carry this around forever, you should pay for it. You should be able to pay for this concept of blockchain rent. So anyway, the general view of this is necessary data, but it's not data we really leverage. And during the course of this project, what we've come up with is a couple real key ways of leveraging this data, and instead of turning it into kind of this baggage, really turn it into an asset. So I'll talk about how we approach that, a little bit how we did it, some of the value that we think can come out of those ideas. I'll first just give a high-level overview of what we built so that you have a context for the conversation. So Fluree is a blockchain graph database. I even got the question today. A lot of people say, well, aren't all blockchains databases? And they are true. They're a little bit different than the context that I'm talking about a database. And when I'm thinking about a database, I'm thinking about like an Oracle or a MySQL or a MongoDB, these generic databases that are used across all industry verticals for all kinds of different purposes. So I think every blockchain is a database as you sort of, in a loose definition, but it's sort of a database with kind of a predefined schema because blockchains have specific purposes. So they already have predefined the types of data in the structure of data that they're going to end up storing. And so I would say sort of the difference here when we created a database is that we allow you to create the schema. essentially you can define the type of data it's going to store, and not to go as far as that, but it's almost like you designing your own cryptocurrency, because you can design that structure. You can design the rules that govern whether or not transactions are allowed or not allowed, and whether those transactions refer to something like coins or tokens, or whether they refer to employees or products. It doesn't matter. You have the ability to define that. So there's kind of two sides of this coin, of course. There's a blockchain side and this idea of this immutable ledger, which, again, the focus here is how do we leverage that history of this immutable ledger? There's the notion, obviously, of consensus. How does a group of nodes agree that a certain transaction or state change is valid or not valid? We approach this from a standpoint that the solution can be run in both a private and a full public mode, so people can launch kind of public databases, but they can also run private databases or databases amongst a network of individuals. And this is in beta, by the way, right now, so people can utilize this. And then, of course, the database side, as I mentioned, we're a graph database, so we allow you to do these sort of analytical queries or even power back-end applications with the data that the blockchain is having, or has. And the part that kind of is the focus here, this notion of time travel, and this really gets into how we can start to leverage this historical context. So what this time travel means for us is that in a typical distributed ledger, you're really looking and can quickly ask questions about the current state. And if you think about a generic database, basically you issue queries, and the queries will respond, and as of what that database happens to know at that moment in time, here's the response. What you're probably not used to seeing in a database is being able to say, well, tell me that, answer that same query for me, but answer it for me as of a year ago, or a month ago, or a day ago. In this immutable ledger, the idea that we have a complete history of every single thing that ever happened actually starts to make this possible. Now it's going to be a little hard to see here, but we've developed some sample applications around this to kind of give some people ideas as to how to leverage this time travel capability within an application. This is just a sample application we built. We call it Cap Table, and it manages a company's capitalization table. It manages their shareholders, it manages convertible instruments, and it manages things like employee stock options. We thought it was a good example to leverage this because lots of companies, and if you've run a company or started a company, you've probably inevitably ended up with a cap table that ends up getting messed up, or people are saying that looks different than the version you gave me at this other time or that other time. So a good example of leveraging blockchain technology to have that proof, have that tamper resistance, and put it to good use. And it's just a simple screenshot. I was just trying to illustrate the time travel capability, but I think this has a laser. Anyway. Well, I guess we don't have a laser. Anyway, we've got just a screenshot of showing sort of stock options and the available option pool. We put a little widget in the upper right-hand corner that allowed you to actually reverse the entire application to any point in time in history. And if you've ever developed an application that needs to report on data in a historical context, it's a lot of work. You usually end up creating additional database tables, you're storing aggregate data in and making all that available. And the idea here is, as a blockchain, we're actually already storing that anyway, so how do we build a technology on top of that that allows you to access that history and access it instantaneously? And that's what we've done here. So if you wanted to, in this case, reverse it to last year, July 20, you can. And from the application standpoint, as far as it knows, it's currently talking to the live database. All that information is coming off of that historical ledger. So no additional development work was really needed to be done by the application engineer in the case of enabling something like this. So this is just a simple example of using something like an enterprise app. What are some other contexts that people are interested in using this type of thing for? One of the largest governments in the world right now is evaluating using this to be able to store land ownership information across the country. The idea that different states can actually run different nodes, so no state sort of controls individual information about land ownership, but works in consensus. But again, the ability to build applications on top of that then that allow you to go instantly back in time and find, okay, who owned this parcel when, et cetera. Again, all that data is there, but the key difference is it's not made readily accessible, and it really isn't treated as an asset in typical blockchains. Obviously, a lot of things around supply chain, people collaborating around parts. You know, maybe someone changes a price and realizes an error and changes it back. You have a complete record of what happened, and you can go instantly back in time to see what the price was at that moment in time when you ran that report, and now the data is coming out differently from the report. So all the data is there historically. One of the questions we get about this is the idea, well, isn't that a lot of data to store, right? You're storing everything. You're putting up these databases that store everything. They have the entire historical context. And I think that's one of the keys here is that storage is so cheap now. And when technology, like a database, has been built, the databases we're used to using, they were built under different constraints that just don't exist today, where storage was really expensive and memory was really expensive. We just don't have those problems. And we can buy enterprise class hard drives now for about $25 a terabyte. Those last, say, 5 years. That's $5 per terabyte per year. And the entire Bitcoin blockchain is about 1/5 of a terabyte today. So not that it's the Visa network, but the entire history of Bitcoin over the past decade or so basically costs you about $1 a year to store. So the storage is incredibly cheap and readily accessible, so it's really not that big of a deal, especially when you have tools that can unlock the value of this historical context information. This will be a really high-level description of it, but how do we accomplish this? And from a technology standpoint and a blockchain standpoint, how do we accomplish getting this historical information readily available? What happens is a transaction comes in, and again, you can define your own schema, whatever you're trying to store. In this case, we're just storing, an individual and like their email address. Here we've updated an email address. It creates logs. So these are a lot like a Bitcoin transaction, which has line items for every transaction that happens, UTXOs, et cetera, all go in there, and the header gets wrapped around it. Same thing, but instead of, again, being sort of a predefined schema, in that case, about transferring assets or Bitcoins from one person to another, here you define the schema. You've defined what you want to store. So those pieces get added, they get wrapped into a block, and then they get appended to essentially a log file. It's really actually a pretty simple structure. And we've come up with the notion that we should run the transactor, the thing that actually changes the state, separately from the query engine. Because when you have an app, you want queries to respond in a millisecond. You want to be able to scale them if you have a high-volume app. So what we do is we actually aggregate and send those updates from the transaction engines to the query engines, which assemble the graph database itself. And you notice here, and we're trying to represent that there's actually different graph databases that go back in time. And the key here is making it quick and efficient to access those historical pieces of information to, again, answer the question, well, what did this look like a year ago? What did it look like a month ago or even a second ago? And how we accomplish that, we actually use some functional data structures underneath where we're really only storing the deltas of each moment in time. So each of those graph databases are actually sharing, 90+% of the core data. So it ends up being really efficient, and even the idea of running, say, hundreds or even thousands of versions of a database on a single application server serving requests becomes easy and efficient. So I know I'm running out of time, and just a high-level overview of sort of how we enabled it. I'll be around if anyone has questions or wants to talk a little bit more about accessing this historical information and doing it quickly and technically how we pulled it off. So, do we have time for questions? Yeah. The question is, are there third parties utilizing the technology in an active way? And yeah, there are. So the technology is actually out in beta currently. So we haven't released it for full production mode, but we have, at this point, over 300 organizations.
Are any of them completely public, and you can talk about it at all?
I don't necessarily want to, the question is, are any of them public, or are there any published use cases? So none that I have permission to discuss, but it's everything from large consultancies, Fortune 500 companies. I gave an example earlier of a large government institution looking to track land ownership or other government records, utilizing it. So it's pretty well, in a lot of startups, utilizing it as a database plus, a database that also has these extra characteristics. Yes? So the question was around federated consensus. One of the things we wanted to do when we designed it, we sort of had the benefit of hindsight that solutions like Ethereum are obviously very public blockchain oriented. And then of course we have things like Hyperledger Fabric, which are very sort of private or federated blockchain oriented. And we wanted to design something that could actually run in any of those modes. And we call it federated consensus because you can actually take individual pieces of data and split up the consensus modes that you're storing it. So if you have one data, I'll use the cap table application we built as an example. Perhaps the public shareholder records you want in a full public database, but the employee stock options, including linking them to the employees' names, you don't. You have the ability to actually treat that as though it's a whole single database powering an application, but actually split up the consensus nodes that certain pieces of that database are around. And we actually bring that all that data together at the query engine side, so we actually kind of allow joins, but joins across databases would be the easiest way to explain it, to aggregate that, even though the data might exist in different consensus modes. And ideas around this has come up with the European Union privacy regulations, et cetera, where you might have data that you want full public, but you can't have personally identifiable information. You could run a private node where you essentially link the personally identifiable information to it. And of course, just by removing the PII internally, even though it's on a public blockchain and it doesn't disappear, it's not identifiable and you can still comply with regulations. So the idea is that you can actually split up your data into these different modes. Yes, sir.
First, great presentation. I love the subliminal brain graphic on the query engine.
Sure.
That's really good. How do you make money? Do you license your technology? Are you going to have an ICO? Do you have a service? How do you monetize this?
The question was, how do we make money? So the database itself, we have not fully open sourced it yet, but it will be open source later this year, so anyone can run it. It's free. It can be modified, et cetera. Again, the focus being, for us, on the use case, being a little bit more towards that enterprise. What we want to make sure we really cater to is these federated networks, so multiple companies running it in a supply chain, et cetera. And companies who are going to run that and run it for business critical processes are going to require support. They're going to want enhanced tools around it to know what all the nodes are doing, if anyone's acting malicious, all that kind of stuff. And those are the things that we'll end up selling. But the database itself is free. Could you just speak up a little bit for me? Are supply chain companies using the products? Using the product today. Again, it's in beta, but there's quite a few proof of concepts going on around supply chain and across a lot of different industries. Retail, agriculture. Again, it's a generic sort of database product, so it's designed to be used across a lot of these different verticals. Yeah, so the question is, how's this different from like a big database companies like an Oracle or maybe a MongoDB or something like that? There's a lot of ways. But from a blockchain standpoint, we are running the database on this true immutable ledger that we give you access to at any point in history. The idea that you can actually run a database that nobody controls. So you can't run an Oracle database that nobody controls. Even if you set up an Oracle database that's going to be shared across 5 companies, one of those companies is running it. Maybe the other companies have the right to audit or something like that, but somebody has it. Here you can define a schema, you can define a set of rules. We actually have a programming language that embeds right into the database functions themselves. Are actually stored as data in the database, but they govern who can update what data under what conditions, and it can actually leverage the full graph database to answer those questions. So I can do something like, if you're the publisher of this product, you can update the description or the price, but if you're not, you can't. And those rules can be established, and these databases can actually run in a way where nobody controls it whatsoever. So, and everyone has complete transparency at all times. So that it would be a core difference from a traditional database.
You just said that no one controls it, so the consensus algorithm, you haven't mentioned what it actually is, the database is using. How do you prevent bad actors from taking over a certain number of those and changing this sort of data?
Yeah, so the question is around sort of the consensus algorithm and how they decide. So there's 2 parts to, and it's the same 2 parts really for most blockchains. One is that you have to successfully process a transaction that everyone else agrees is the transaction that you processed, and the second is something that gives you the right. In the case of Bitcoin, it's proof of work, or proof of stake, something that gives you the right to mine the block. So you got to be able to do both those things. For us, it's another way of leveraging the historical context. We use a variation of proof of capacity. So it's a lot like proof of work. We're basically going through and we're sort of pre-computing the possible solutions, and those get stored on a hard drive. The key here is we're actually using the database data itself as the seed for those possible block solutions. So you're actually encouraged to store as much database data as possible, because the more database data you actually store gives you more chances to mine a block as those blocks come up. So, I talked about leveraging the historical context of the data from a time travel standpoint. We also leverage it from that standpoint. The more of that data that you can basically prove you have, the more of a chance you get to mine a block. And that's what encourages people to store the data. When people want to transact data, essentially they're attaching transaction fees. And those transaction fees are going to the miners that are processing those transactions. The result of the transaction are these, we call them flakes, but essentially these log items, which then all the other nodes end up verifying. A transaction only succeeds if the rules inside the database allow it to succeed, and every node, it's deterministic. Every node would come up with the same result, that no, this is an invalid transaction, this is a valid one. Yes, sir? Yes? What happens if someone gets a monopoly over the data? Yeah, so you have the ability to pay people to mine the database. And how much you pay people to mine the database is going to directly control how much consensus you're going to end up having around the database. So getting back to kind of one of the core use cases here of running it in a federated node, if I have 20 people in a supply chain network, for example, I can actually lock down to those 20 nodes that those are the only ones who can participate, and therefore the network can't get overwhelmed because you can't have new actors essentially come in and assume those identities. So that part's locked down. They can still utilize a consensus method internally to determine who, randomly basically determine who gets to mint blocks, but the situation is locked down. The public version of FlureeDB basically runs as each database is essentially a side chain. So that's sort of the model. So there's kind of a core backbone, and every database is a side chain. Depending on how you're funding that database is going to determine how many nodes are going to end up participating in leveraging that data and processing your transactions. So you're actually in quite a bit of control over how much consensus happens around it. One of the exciting things we really like with this model is this idea that people could launch a public database that maybe people really care about the data, like global climate change data, human genome data, and actually offer people no money to mine the database, but because you may believe in that cause and you want to support this global database of this information, you may choose to end up mining that as well. But you control the economics, and those economics will end up determining the amount of consensus that participates in these side chains. Yes, sir.
So if you have a database that generated an audit trail, could you go back and incorporate that into there so you have a longer time series?
Yeah, if I understand your question right, if you have a database that has a historical time or historical context, could you sort of pull that into another thing, another database, or extend it? And the answer is yes. You can never modify a database, but you can fork a database at any point in time. Technically, it becomes a new database, and we allow a notion of aliasing. So your applications might be talking to, database A and database B. Under the hood, those are actually aliases to some database ID. So you can fork a database at any point in time, apply new transactions to it, actually move the alias over, and then any applications leveraging it, they don't have to change at all. But technically, at that point, it is a new database. It's not the same database. Got time, I think, for one more here. Yes?
What's your definition of a transaction and the cost associated with the transaction?
Yeah, great question. So the question is, what's the definition of a transaction? What's the cost associated with it? So we've designed this to act like a general purpose database. So a transaction is a set of state changes that you want in the database to all happen together. And it is an ACID compliant database, meaning that those transactions will all succeed or fail together. They will never partially succeed. So it's really focused on, again, being ready for enterprise type of use cases. So it's whatever you want to change. It can be a lot, or it can be a little simple piece of information, but that is a transaction. What's the cost associated with it? It really only applies from a pure public blockchain standpoint, and the economics end up driving that decision. So it's in beta right now. We have not launched the public version, so I don't know what those costs will end up being. When you're running it in a federated node, you have, like I said, 20 companies doing it. They could associate some sort of cost for that internally, but there's sort of a general assumption that those 20 companies already have a stake in maintaining that particular piece of data, and there probably doesn't need to be an additional economic incentive for it. And that is it. So thank you very much. I appreciate it.